questions about anything from last time? Yeah?
Not from last time, work number 15 on 179. It just showed that if derivative of function is bounded on an interval, then f is Lipschitz on that interval.
Aha.
How would, k is just the supreme of the absolute value of f prime, I think. But how would you show that without like a picture?
So let's see, what was that problem was, you said, page 179 what?
Number 15.
A big hint is the mean value theorem. Right, because, let's see, the mean value theorem would give us f of b minus f of a is over b minus a is a f prime of c. So you take your x1 and your x2, you let a equals x1, b equals x2, and then when you there'd be a c between x1 and x2, and you play around with that and realize, oh yeah, the biggest that constant could be in the Lipschitz estimate would be the maximum of the derivative, because it's f prime of c, and if that's bounded, then you can bound the Lipschitz constant by that. Does that answer your question? Yeah. Let's see. So, exciting moment here. We're going to shift gears and start talking about integration, and especially the Riemann integral. And I'm going to, and this course is sort of traditional to do it in a different order. And in fact, that's the way I learned it. 7.4 introduces something called the Darboux integral. And the Darboux integral is equivalent to the Riemann integral. So, and it's somehow, for me, it's cleaner and nicer, and the results are much more transparent, to me at least. And I think you'll find that other sections are doing the same thing and changing the order here. Okay, so that's important. Also, read the stuff about convex functions and Newton's method. And that's section 6.4 about the Taylor's theorem. And I'll come back to that later in the semester, but in the meantime, that's important to read it. So it's always been very important to read the book as I lecture. My lecturing is supposed to make it easier to read the book. And yeah, okay, that's the important thing. And so before I launch into Riemann integration, I thought it'd be fun to do some history of the subject. Riemann, well, Newton and Leibniz both thought about areas under curves. So Newton and Leibniz, in fact, Leibniz invented the symbol for integral. And Leibniz was the one who came up with this S for sum, f dx. And of course, they were thinking in terms of Riemann sums. To get the area under curves. But in the 1800s, Riemann started thinking about making the subject more rigorous and demonstrating the facts. Like we have been in this class, understanding the foundations of real numbers and how it relates to integration. So Leibniz and Newton had kind of wishy-washy ways of talking about what an area under a curve was and how it relates to this thing, integral involving Riemann sums. And so Riemann made it rigorous. And then later, Darboux, or the same person with the Darboux intermediate value theorem for f prime, read Riemann's paper in German and translated it into French, and then started working on integration himself and improved the definitions. And made them sort of more mathy. And a fact is, his definition, so we call those, they call that the Darboux integral, exactly the same as the Riemann integral. And the functions that have a Darboux in an integral and a Riemann integral are exactly the same. So it was just an improved way of talking about this subject. But the Riemann integral was found to be defective. Back in that time of Cantor and slightly after Riemann, mathematicians started studying Fourier series intensely. And there, wild and crazy things start happening. Functions can be pretty weird, and convergence can be pretty weak. And it was disappointing that the Riemann, sometimes functions would converge, but the Riemann integrals wouldn't make sense of the limit. That was a bummer for everybody. Anyway, later in the business, another French guy, Lebec, Henri Lebec, with the G, came later and improved the Riemann integral. And he invented measure theory, which was an important advance. Okay, and I guess I want to say a few words about Lebec. In the classic example of a function, f of x is 1 on the irrational numbers and 0 on the rational numbers. And then it was bugging people back in the time of Riemann. What is the integral from 0 to 1 of f of x dx? That integral does not exist as a Riemann integral. F is not Riemann integral, but it is Lebec integrable. So the Riemann integral doesn't make sense. But it is Lebec integrable. And you ask yourself, what should it be? Well, we know there's a lot more irrational numbers than there are rational ones. So the set where it's 0 is much smaller than the set where it's 1. It turns out, from the point of view of measure theory, the set of irrational numbers in 0, 1 is a set of full measure. Its length is 1. And the set of rational numbers is a set of measures 0. So you think of its length as being 0. So the Lebec integral, that integral equal 1. For the integral being the Lebec. And I'll say a few words about why that makes sense. you think about the rational numbers. Q. I can pick let's let epsilon be bigger than 0. And here's a rational number, Q. Let's call it, we're going to count the rational numbers. We know they're countable, so let's call it Q sub n. And then I take a little interval about Q sub n of length. Let's see, what's the length of this going to be? I want the length of this interval to be epsilon over 2 to the n. So I'm going to choose this length to be epsilon over 2 to the n. So the epsilon is small, and when I divide it by 2 to the n, it's even smaller. Okay. And let's call that green interval I sub n. It's an open interval of length epsilon over 2 to the n. And we see that if we let's enumerate the Q sub n's as n goes from 1 to infinity are the rational numbers um, 0, 1. We know they're countable. And now if I take these the union of those things, I see that, and this is what Lebesgue realized, those rational numbers, so Q intersect 0, 1. I guess I should include 0 and 1 there, rational. It only adds 2 to the mix. Q intersect 0, 1 is contained in the union of those little intervals. And that's a really small set from the point of view of length. So if you ask yourself, what's the length of that set? So those sets might overlap. So we would expect if the length to be less than or equal to, probably less than, the summation of the lengths of those things. Epsilon over 2 to the n as n goes from 1 to infinity. And that's equal to epsilon. That sum is equal to epsilon. So with Math 341, we study epsilons and deltas. When you do measure theory, you have to do something more sophisticated. You have to study epsilons over 2 to the n's and add up a whole bunch of small things and still get something that's small. And that's the classic definition of a set of measure 0. It's contained in a union of intervals whose total length is as small as you like. So the word is that the rationals are a set of measure, here's the word, Q intersect 0, 1 is a set of measure 0 in the sense of Lebesgue. Because I can make that epsilon as small as I want. And so we expect the values of the function on a set of measure 0 not to affect the integral. And the irrational numbers, the complement, namely the irrational numbers, is a set of full measure. So measure 0 is a word that would be defined later in Lebesgue theory, and full measure means it's everything except a set of measure 0. And the full measure would be 1. Okay. And so the function is 1 on a set of full measure and 0 on a set of measure 0. So it's 1 times that length plus 0 times 0 length. And that's what Lebesgue thought of. So he thought of, instead of doing Riemann sums, he's sort of cutting up the values of the function and thinking of the set of the measure where the function takes certain values, the length. And that's sort of a backwards way of doing it. But it was necessary to understand sort of fine points of what length and area are. So that's an exciting advertisement for a future graduate level course in measure theory. At Purdue, that course is 544, measure theory, real analysis and measure theory. And so what we're doing is a prereq for that. So before you can understand Lebesgue integration, you need to understand Riemann integration. And as long as I'm going to do history, I might as well go back to Archimedes. Good old Archimedes. Somehow Archimedes figured out the area under a parabola. Using the type of reasoning back then that was very geometric. Okay, and the historical documents are interesting to see because he uses the language of the time in terms of kind of Euclid reasoning. And of course, when you calculate areas, you have to do calculus, you have to do sums and infinite series. He was thinking in those terms, even though he tried not to write in those terms. And so the classic example I always do in freshman calculus because it's just plain fun. Let's see, I can make a big picture here. Is to find the area under the graph of y equals x squared between 0 and 1. Okay, and the classic calculations are, let's see, first, color. I'll take the left endpoints and do a Riemann sum. So I'm going to cut up the, this will be a 1 over n, a 2 over n, a 3 over n, etc. Maybe one more. 4 over n, dot, dot, dot. And n is equal to n over n. The last one. Oh, I wish I'd made that n a capital N. Okay. And if I take the left endpoints and do a Riemann sum there, I would get, let's see, there's the left endpoint, left endpoint, left endpoint. I get, the first one would be have 0 height, so it'd be a rectangle of 0 area. The next one has a little bit of height, and the base is 1. The next one has more, etc. So that's the Riemann sum with left endpoints. The area under that thing is clearly smaller than the area under the graph. So let's see, the last one here would be this would go up like this and go up, be underneath the integral from 0 to the area from 0 to 1. Okay, so the sum of those areas is going to be less than what we expect the area to be, if it makes any sense at all. Okay, and then if you look at the right endpoint version of that thing, I'll make it orange. Then you'd get some, let's see, if I take the right endpoint instead of the left endpoint, I'd get a rectangle with some height on that first one. Then the next one would be that one, that one, that one, And the last one here would be this one. Try to make it look better. Okay, so the green ones are less than the area, and the orange rectangles, the areas add up to something that should be greater than the area. And so let's see. Let's let A equal the area under the curve. And of course, we're thinking integral from 0 to 1 of x squared dx, which we know how to calculate by the fundamental theorem of calculus. That's 1/3 x cubed evaluated between 0 and 1, and that's 1/3. So we're thinking we're going to get 1/3 when we think about this hard. Well, the sum of those green rectangles are underneath that, and let's see what I can actually write that out. What are those? I have the height is 1 over n's. It's going to be let's call it n over n squared. That's the height of those little rectangles, starting with n equal 1. That would be the first one's 0, so it doesn't count. The next one, starting with n equal 1, would be n over n squared times the delta x, which is 1 over n, 1 over capital N. Okay, that's the delta x from freshman calculus. And this is the f of xn in a Riemann sum. Okay, that's clearly underneath the area, so it's going to be less than the area. And now the orange stuff is clearly above the area, so that's going to be bigger. And that sum, let's see, the first one would be, that's the right, let's see, how far do I go? The green ones go up to n minus 1. Because I'm doing the left end points. But the orange ones start with 1 and give me n over n squared times delta x. Delta x is 1 over n. And how far do they go? Let's see. The last one there is capital N. So those two sums are really close together. One's underneath, one's above. And in fact, if I subtract the difference from them, I see that they're tending to the same thing. Right? So, what's the difference between this right sum? Let's call this an upper sum, U for upper, and L for lower. U minus L include all the same terms except for that last one. U minus L is n over n squared times 1 over n. So the stuff above and the stuff below are getting really close together. You had an exercise where you showed that that means those sequences actually converge to a value. And in fact, we in the first section of the class semester when we were studying mathematical induction, let's see, what is that thing going to be there? That left-hand sum would be a 1 over n cubed. The sum as n goes from 1 to n minus 1 of n squared. That's less than a is less than 1 over n cubed times the sum as n goes from 1 to n of n squared. Oh, blast, I didn't write. What's the famous sum of that series? Anybody remember? N times n plus 1 times n plus 2 over something? Maybe 3? It's got to be 3, right? Because we're going to get 3 for an answer. Have to go back and look in section 1.2, wherever we did induction. What's the answer? Oh, blast. So it has the... Oh, there it is. Oh, 1/6. Oh, yeah, here it is. Section 1.2, we did the classic induction and saw that this is 1/6 times n times n plus 1 times 2n plus 1. That's where this 1/3 is going to come from. Okay. And once we know that, then on this side, we get the same thing, except we're adding it up to n minus 1. So this would be 1/6. And in place of n, I'd have n minus 1. N minus 1 plus 1 would be n. And then I'd have 2 times n minus 1 plus 1. And I'm dividing those two things by n cubed. So if I distribute the n cubed through both sides there, I would get 1/6. See, when I divide by n cubed, I'll distribute n cubed through those three terms and get 1 minus 1 over n. N over n is 1. And then I get 2 times n minus 1 over n plus 1 over n is less than a is less than, and here I would get 1/6, 1, 1 plus 1 over n, 2 plus 1 over n. And it's very easy to see that those both sides tend to 1/3. So let n go to infinity. And now we know the squeeze theorem. One-third less than or equal to a is less than or equal to 1/3. So that means the area makes good sense, and it's exactly what Archimedes discovered it would be, 1/3. Okay, well that's the whole idea of Riemann integration. Those things are Riemann sums. And you can read about Riemann's version in section 7.1. And Riemann integral would be the limit as n goes to infinity of Riemann sums. And it wouldn't matter if you take the left-hand endpoint or the right-hand endpoint. And of course, for that Riemann integral to exist, you need a pretty nice function, maybe. X squared is a wonderful function. It's continuous, for example. In fact, continuous is enough. It's also differentiable. But you don't need differentiability for integration. Okay, so that's section 7.1, talks about Riemann's historical way of doing it. But we're going to do Darboux first. Start with Darboux' version. In 7.4. Okay. So let's see, what's Darboux' version? You know, y equals x squared was a monotone increasing function. That's what made the left endpoint interesting and the right endpoint interesting. The left endpoint was the minimum on an interval, and the right endpoint was the max. Okay, and Darboux was realizing sort of that's the crux of the argument of Archimedes. So here's what Darboux did. Instead of delta x equals b minus a over n, we partition. Partition, so that's a word. Partition, we're going to do an interval AB into intervals. And they don't have to be all the same length. That kind of simplifies things later down the road. Okay, so a partition is going to be, you'll have A will be, let's make A be x naught, and then we'd have x1. Then we might have a long x to x2, short to x3, dot, 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 and B would be equal to the xn. The last one. And that's going to be a partition, which I'll call script P. And when you graph your function on that, let's graph f. I'm going to make it wiggly. I'm going to do a lower Riemann sum and an upper Riemann sum. The lower one, I'm going to take the inf on each interval. So this is going to be my green one here. On this first interval, here's the inf. And on the orange one is going to be the soup on that interval. Oh, I kind of chose a weird, looks like the soup is right here. Okay, that's the soup on that interval. On this one, oh, where's the inf? Looks like the inf is over here. But the soup on this one is right here. Etc. So here's the inf again, being a nice min. The max on this one looks like it's the left endpoint, etc. And on this last one, here's the soup. And here's the inf. Okay? Okay, a lower sum. A lower sum is going to be equal to, I'll call it L. It depends on the partition. Depends on the function. My green graph there is y equals f of x, not green, blue, f of x. Okay, let's see, that's going to be the sum as n goes from 1 to capital N of the infimum. So I'll call that infimum, kind of like a min, m sub n times the delta x, but the delta x's are all different. So that would be xn minus 1. Okay, so you think of that as the delta x in the Riemann sum. But now this thing is mn is equal to the inf of f of x as when x is in that interval. That would be xn minus 1 to xn. Okay, that gives you the area underneath the green stuff there, which is clearly too small for the area. And then the upper sum can be the same thing, except with the soup. Upper sum. That would be capital U of it depends on the partition and the function. It's the same thing, but this time we would have some from same stuff, but capital MNs, which are going to be like the maxes. And here, the capital MN is the soup. The soup of f of x. Of course, if f was continuous, the nth in the soup would be the max and the min. I should say the min and the max. Okay, so here's some fascinating, easy lemmas. So here's an important fact. Oh, see, I should define what it means to be. I should define what it means to be Riemann integrable. Oh, let's see. Here's some various definitions. It turns out that all the L's are less than or equal to all the U's. That would be a lemma in a minute. It's not a hard, it's a very straightforward, easy lemma, which I'll show you. So an easy fact in a minute. Fact. L of a partition, P1 of F, is less than or equal to U of any other partition. So for any partitions, P1 and P2. That turns out to be relatively easy to see. And therefore, let's see that we pick a partition on the right, P2, that shows that all those lower things are bounded from above. And picking a partition P1, that shows all the things on the right are bounded from below. Okay, so let's let definition L of F is going to be the soup of those L, P, comma, F for partitions P. So I'm taking the soup over all P. They're bounded from above by that easy fact. So that soup exists and is finite. And then the upper one, upper limit, I guess you'd call that the upper area if you wanted to. You have a lower area and an upper area. And that would be the nth of those upper sums over all possible partitions. Okay, and now finally the big definition of what a Riemann integrable function is. By the way, if f is bounded, these things all make sense. So here's the easy fact. Fact. F bounded implies all this stuff makes good sense. LF. Let's see, all those things on the left are less than or equal to all the things on the right. So notice that an easy fact is L of F is less than or equal to U of F by the properties of ints and soups. That's an important fact. Easy fact. So f bounded implies L of f and U of f exist. And now the definition of a Riemann integral, a bounded function, f is Riemann integrable if L of f equals U of f, like in the case of the Archimedes example. And we write, if that's the case, the integral from a to b of f dx equals that number, whatever it is. Okay, that's the definition of Riemann integrable function. And I guess the thing I can do in the last 10 minutes here is show you those easy facts. So that definition will make sense. And read the book carefully for the easy facts. I'm going to give you picture proof of it, kind of. So here's the easy facts. Well, here's how to make them easy. Step 1, show that if you toss in a new point in a partition, step 1, if you add a point to the partition, let's suppose we have a partition, we have P1, get P2 from P1 by adding a point. Get P2 from P1 by tossing in another point. X in the partition. X something. X sub n plus a, stick one in there. Adding a point to the partition P1. A single point. I guess I should emphasize single point. Okay, so what could that do to the lower sum and the upper sum? It can only make the lower sum go up and the upper sum go down. So I claim the lower sum, the worst that could happen is it might go up. It might not go up, but it might go up. Okay. And of course, we know that the lower sum, we know this one is less than the upper sum for P2. And the only thing that this is a new one, and this is, we already know this one. But the fact that will be easy to deduce here is that the only this thing that this can do is go down when you toss in a point. Okay, that's easy, and it's just a picture proof. Let's see, how would I do it? I'd have an interval here. Everything else would stay the same, but I'd have a xn minus 1 and an xn, and I'm tossing in a new point here, x, call it x prime. I'm tossing that in. And so let's see if I, think of the min here, oh, should I make it have a hump? Why not? There's my function. A lower sum would be, for the whole thing, let me make it have a, why do my functions always? Okay, a lower sum here would be this and this. What? Oh, this would be the lower sum for the whole thing. Okay, that's the whole thing, lower sum. But when I add my new point in here, I'll make this a dotted line. Then my second lower, that's what my upper sum would be this. Okay, so how much would it change when I do it again? Let me I have a fancy unit here. I'll copy this picture. Okay, so we see we have a lower area and an upper area there. When I cut it up and do it again here, I'd get some more. I'll make it dotted. That would still be the lower sum for that one, but then this one would have a new lower sum. So I'll make it green. So it would add a little bit. So you see, in that case, it goes up. And in the case of my upper sum, oh, how could I be so stupid? I made my max at the point. That was dumb. Let me move my x prime over here. Oh, blast. Okay, I'm going to move my x prime over here. X prime. Okay, that's correct. My left-hand picture is still correct. But now my right-hand picture, let's see, this is my new lower sum. My lower sum gets bigger. My upper sum is going to get smaller. Let's see, what would be the new smaller upper sum? The max on this first interval would be achieved here. And the max on the second interval would be the same. So that, I guess I'm killing this, or overkilling it. It's not hard to see that, oh yeah, if you add more things, you're going to add little pieces of area there that are only going to make it bigger. And of course, there are some cases where it doesn't change, because there might be maxes and mins that are in just the right spot. Okay, so that's easy. And now, so if you have two partitions, you do this one at a time. If you have two partitions, you compare, you let P be the union of the partitions. And then you use this fact to see that L of P1 F would be less than or equal to the union I could toss in those points one at a time and get those inequalities. And then, so that would be true. And then I would know that this one is less than or equal to U, P, F. And this one would be less than or equal to the U, the other one, P2, F. So every lower sum is less than or equal to every upper sum. So think of this